Vice President Xia, Dean Wang, Professor Shui, ladies and gentlemen, it's a tremendous honor for me to be here as a guest professor of Tsinghua University. But before I go on, I want to express my sympathy to the people of China for the terrible tragedy that occurred in Sichuan province and that is still going on there. I know that the thoughts and the hopes of all the world are with the people of China at this very difficult time. I've had the great benefit of a long association with this university and with China more generally. I first came to China in 1984, before most of you were born. I've been here at least once a year, every year since 1984. I have had the benefit of collaborations in research and analysis of policy with many Chinese colleagues, focused on energy issues, on environmental issues, on nuclear arms control and non-proliferation issues, on science and technology policy. We have had the great benefit in the Kennedy School of Government of having senior visitors from Tsinghua University. Most recently, Professor Shui Lan has been with us. Dr. Su Jun was with us earlier. One of his students, Ru Peng, was just with us in the Energy Technology Innovation Project. And one of my many hopes for my new role as a guest professor of Tsinghua University is to build up these forms of cooperation and exchange to even higher levels, to have more people from Tsinghua coming to visit Harvard, more people from Harvard coming to visit Tsinghua, and more genuinely joint projects in which we work on subjects of common interest, write papers and reports together, and present them to the policymakers in our two countries together. Because, as I will describe at greater length in my main lecture, our two countries have a great deal in common in spite of their differences. We both face tremendous challenges in the energy field and in the environmental field, and above all, at the intersection of energy, environment, and economic prosperity. And the solutions to those challenges can only be found if we work together on them. So I take this tremendous honor of the joint appointment, the appointment as a guest professor at Tsinghua University, as a huge opportunity as well as an honor to continue to build the cooperation between our universities and indeed between our countries. Thank you very much. All we have to do is get this in there. Is this the one? I guess I'll stand up on this. Well, thank you again. I'm going to try to cover a lot of ground in this presentation. And as a result, I may from time to time speak too rapidly. If I do, I apologize in advance. And the only good news is that I'm sure that a copy of the presentation is in front of you. And so if there's anything that goes by too quickly, you can look at it further in what I sometimes humorously refer to at Harvard as your abundant free time. I want to start with the question of the science of climate change, what we actually know about it. I'll talk then about the technology with which we could respond to the climate change challenge, what can we do. A little bit about the economics, what can we afford to do. And finally, a bit about the policy issues of what is the best way to move ahead in addressing this challenge. To start with the science, we really need to start with understanding what the climate is. Many of us are accustomed to hearing this challenge described as the challenge of global warming. But global warming is really a misleading term with respect to the character of this problem because it implies that it's only about temperature. And in fact, temperature is only one feature of the climate. In fact, we should really think of the average surface temperature of the planet as an index of the state of the climate as a whole. And the climate as a whole is the pattern of the weather. Weather is what is happening outside here and now, whether it's sunny or cloudy, whether it's hot or cold, whether it's raining or not. But climate is the pattern of those things, what you expect over time, the averages, the extremes, the pattern in time, what times of the year does it rain, what times of the year is it hot. All of that, cloudiness, humidity, rainfall, snowfall, the patterns of wind, the frequency of storms. And when you change the climate, you change the pattern. You don't just change the temperature. Very small changes in the temperature, in fact, correspond to large changes in the pattern. The difference in average surface temperature of the planet between an ice age and a tropical period between ice ages is only about 5 degrees Celsius. 5 degrees is all of the difference between a tropical world and a frozen world. So you should not ever misunderstand the seemingly small temperature changes that are discussed in the context of global climate disruption and imagine that these small changes are not significant. We know that the Earth is in fact getting hotter. This is a graph of 125 years of the average surface temperature of the Earth. This goes back about as far as there were enough thermometer measurements around the Earth, both on the oceans and on the land, to meaningfully define the average. Before that we had thermometers, but we didn't have enough thermometers used often enough to really know what the global average surface temperature was by direct measurement. We can sometimes figure out what it was likely to be from other kinds of evidence, but this is what is often called the thermometer record of the Earth's temperature. 2005 was the hottest year in that 125 years. 2007 was tied with 1998 as the second hottest year. The 14 hottest years in the 125 all occurred since 1990. 24 out of the 25 hottest years in the last 125 years all occurred since 1980. If you are a statistician, you can calculate in the margin of your notebooks how improbable, how unlikely it is that such a pattern would occur at random, rather than as a result of some systematic influence on the climate system which is causing it to heat up. In fact, we know what the systematic influence on the climate has been that is causing it to heat up. These are the estimates of the Intergovernmental Panel on Climate Change on what has been influencing the climate over the last 255 years, from the reference point in 1750, which is by convention taken as the benchmark, to 2005. These are what climatologists call forcings of the global climate. Forcing literally means how hard are you pushing on the climate with some influence, whether natural or human-made, that is having an effect on the climate. And you don't really need to care about what these units mean. They are watts per square meter averaged over the whole surface of the Earth. But the important thing here is the relative size of these numbers. The biggest of the forcings by far over this period was the accumulation of carbon dioxide in the atmosphere that was put there primarily by burning fossil fuels, coal and oil and natural gas, and by deforestation, cutting down trees and burning them and adding their carbon to the atmosphere as carbon dioxide. There are a number of other influences, other heat trapping or greenhouse gases, methane, nitrous oxide, chlorofluorocarbons, black particles, soot, which warm the atmosphere and the surface of the Earth, also a warming effect. And there have been some cooling effects. The minus numbers are cooling influences on the climate, particles that reflect sunlight back to space, particles that form clouds that are white and also reflect sunlight, changes in human land use. The biggest natural change over this period has been a small change in the amount of energy reaching the Earth from the sun. That's the very bottom line here. And what you can see is that the magnitude of that change in energy reaching the Earth from the sun is about 1/15. 1/15 as big as the magnitude of the carbon dioxide, about 1/30th as big as all of the human influences combined. So although some people will still tell you that what we are seeing is a natural phenomenon and it's just the variation of the sun, that position is absolutely inconsistent with the scientific measurements. The scientific measurements show that overwhelmingly it has been human activity which have created most of the forcing, most of the influence on the climate over this period. Perhaps the most compelling evidence that we understand what is going on is this two-panel presentation. This is the same 125-year period you saw before, 1880 to 2005. Plotted in the top are our best understanding of the various forcings as they have varied over time during this period. The red line, rising rapidly above everything else, is the greenhouse gases, carbon dioxide, methane, and so on, that have been added to the atmosphere mainly by human activity. The blue line that bounces up and down on the bottom are volcanic eruptions. This is a natural effect. When a volcano erupts, it injects reflecting particles into the upper part of the atmosphere, and they cool the Earth for a while. The middle lines are these various other influences described on the previous slide and labeled here. And the interesting point is, when you provide these influences as input to a modern computer model of how the climate works, what comes out of the computer model is what you see at the bottom. What you see at the bottom in blue are the actual temperature measurements made by thermometers over the last 125 years. And what you see in black is the average of 5 computer runs computed based on the forcings that are shown at the top. And as you see, the match is essentially perfect. Our current understanding of how the climate works, embodied in state-of-the-art computer models, almost perfectly reproduces the temperature history of the last 125 years when you provide to that computer model the known influences on the climate, largely human influences over that period, but also including all the natural influences as we understand them. The heating, of course, is not uniform geographically. The Earth heats unevenly as a result of these influences. It heats more over the land and less over the ocean, and it heats more in the far northern latitudes than near the equator. This is a plot of the distribution geographically of the temperature increases just in the period from 1950 to 2005. The average temperature increase for the world in this period was 1/2 degree Celsius. But as you can see from the scale, the increase in the temperature in the middle of the continents was often 1 to 1.5 degrees Celsius, or 2 to 3 times the global average. And the temperature increase in the far north was often 2 degrees Celsius or more, namely 4 times the global average. Now, this non-uniformity in the heating is very important because it causes changes in the circulation pattern of the atmosphere. It changes the pattern of the winds because the winds are driven by differences in how much heating there is on different parts of the Earth's surface. And here is an example of particular relevance to China of how those circulation patterns have been changing. This was research done here at Tsinghua University showing the weakening of the East Asia monsoon over the last 35 years. That monsoon has been weakening steadily, as you see from this diagram, and the observations in the weakening of the monsoon match almost perfectly the predictions by Chinese researchers of what is expected under warming of the Earth driven by greenhouse gases. Those changes in circulation patterns are already having adverse impacts. In China, the weakening of that monsoon means that less moisture flows in the atmosphere from south to north, and that produces increased flooding in the south and increased drought in the north, which of course is a big problem for China. This is not a problem of the future. This is not a projection. This is something that is happening already in China as a result of global climate change brought on mainly by greenhouse gases. This is another picture from our colleague at Tsinghua University emphasizing the point that extreme weather events become more likely under climate change. Scientifically, you cannot point to a single flood, a single storm, a single drought, and say that climate change caused this. Because, of course, there were always floods, there were always droughts, there were always storms, and you don't know whether a particular one was really caused by climate change or not. But what you do know is we are changing the probability. Another way of saying this is we are loading the dice. We are increasing the chances of extreme events through our influence on the climate. And we can expect, therefore, to see more of them as climate change goes on. Major floods, in fact, have been increasing on every continent. This is the history of the last 50 years of flooding on every continent, decade by decade, starting in the 1950s. And you can see that extreme floods, major floods, are sharply up everywhere, but above all, they are most increased in Asia. Droughts are also increasing, and some people wonder how this can be. How can it be that a single form of climate change could make it both wetter and drier at the same time? But the reason is actually quite simple. In a warmer, wetter world, a larger fraction of the rain falls in extreme events. More of that rain runs off to the sea rather than being absorbed by the forests and by the soils, and the periods between extreme events become longer. And therefore, even though you have more rainfall altogether, you have more drying out between the rainfall, and you get more drought. I'll say more about this in a moment. Regions that are prone to wildfires are experiencing more wildfires under climate change. This is a graph for the western United States, where the number of wildfires has increased fourfold, 4 times, in the last 30 years. Keep pointing in the wrong direction. In the meantime, there are lots of other indicators of what's happening. Glaciers are shrinking all around the world. This is a before and after picture of a major glacier in Alaska, 1941 and 2004, taken from exactly the same position. And you can see the glacier has practically disappeared. That is also happening in the Tibetan Plateau, in the glaciers that feed China's great rivers. By some estimates, those glaciers are now shrinking at 7% per year. That means the half-life of the glaciers is 1 decade. The Arctic sea ice is also shrinking. What you see here is based on satellite imagery from the National Aeronautics and Space Administration in the United States. The magenta line is the average extent of sea ice in the Arctic in the late summer, this is September, over the last several decades, during which time we've had the satellite observations to determine the extent of the sea ice. On the left, you see how much smaller the sea ice was in the late summer of 2005 compared to that long-term average. And on the right, you see what happened in September of 2007. It completely broke the 2005 record, astonished everyone who studies Arctic sea ice. Before 2005, most of the people who study sea ice estimated that the sea ice might disappear entirely in the summer by perhaps the year 2070. When the September 2005 data came in, and people looked at how much the sea ice had shrunk, they said, maybe we were wrong. The sea ice could be gone by 2040. When 2007 came along, and the enormous shrinkage of the sea ice that you see in this picture became known, the scientists looked at that and they said the sea ice could be entirely gone by 2013. A drastic acceleration of the rate at which the sea ice is disappearing. The reason this is important is not sea level. This is floating ice, and when it melts, the sea level does not increase. However, what does happen is the reflectiveness of the Earth's surface drastically decreases. Something that was white and that reflected most of the sunlight that hits it now becomes blue and absorbs most of the sunlight that hits it. That drastically changes the energy balance of the entire Arctic. That drastically changes the entire climate of the northern hemisphere. Nobody knows for sure what the full consequences of the disappearance of the sea ice would be, but they are expected to be drastic in terms of circulation patterns. Meanwhile, Greenland an ice sheet that is land-based and that does raise sea level when it melts is increasingly melting. These diagrams, these actually satellite images, show the extent of surface melting of the ice on Greenland in July of 3 different years, 1992, 2002, and 2005. And the areas in red are the areas where the ice is melting at the surface in Greenland. And you see it's drastically expanded. And in 2007, for which there is not yet an image available in this same format, the data show another 10% reduction below the 2005 level. So this expansion of melting in Greenland is continuing. That is contributing to sea level rise. Keep going in the wrong direction here. And sea level is in fact rising. These are now direct measurements of sea level increase. And what you see here is that over the last decade or so, the rate of increase of sea level is about 3 millimeters per year. That doesn't sound like much, but that's 30 centimeters per century. And it's accelerating. It's now about twice the rate as the average for the 20th century. And it's expected to continue to accelerate. The current best estimate of how much sea level will go up in the 21st century is about 1.5 meters, but that may still be an underestimate if the rate continues to accelerate. In terms of direct impact on the life and health of people, climate change is already taking a toll. The World Health Organization estimated that already in the year 2000, climate change was responsible for more than 150,000 premature deaths per year. Those were coming from heat waves, from floods, from droughts, from expanded geographic range of malaria and other climate-related influence. That was in 2000. The World Health Organization will soon come out with a new estimate for more recent years, and it is expected to be much higher. If we continue on the business as usual trajectory, if we keep doing things in the world the way we have been doing things, only bigger, we are heading for much larger disruptions of climate. What you see here on the left in black is the historical temperature record. What you see on the right in various colors are the different scenarios produced by the Intergovernmental Panel on Climate Change on what could happen in the future under different assumptions about population growth, economic growth, and technological change. The gold band, the lowest of the ones on the right, is what would happen if you could stop all change in the atmosphere instantly. If there were no more accumulation of greenhouse gases in the atmosphere after today, the temperature still continues to increase. That's because of the time lag connected with the very large heat capacity of the ocean. What that means in everyday terms is it takes the temperature of the ocean a long time to catch up with changes in energy flow that you have imposed on the atmosphere. And so even if we could stop right where we are in terms of the concentrations in the atmosphere, the temperature would still go up ultimately by about another 0.5 degree Celsius. But of course we have no way to stop instantly where we are. And so all of the IPCC projections for what will actually happen over the next century are much higher. The European Union decided in 2002 that a prudent goal, a responsible goal for the planet, would be to try to avoid exceeding a temperature increase of 2 degrees Celsius above the 1900 level. And that 2 degree sea line is drawn there in black. And you see that under a mid-range scenario of the IPCC, the world would cross through that 2 degree sea line around 2050, and by 2100 we would be at 3, maybe even as much as 4 degrees Celsius above the 1900 level. And it is kind of interesting to know that the last time in geologic history the world was 2 degrees Celsius above the 1900 level was 130,000 years ago. That BP means before present. It doesn't mean British Petroleum. It means before present. 130,000 years ago, the world was about 2 degrees C warmer than in 1900. And at that time, sea level was between 4 and 6 meters higher than sea level is today. The last time the world was 3 degrees Celsius above the 1900 level was 30 million years ago. At that time, sea level was 20 to 30 meters higher than it is today. What is coming in this world of business as usual? More heat waves are coming, for one thing. This is a rather elaborate diagram, but I will summarize it very quickly by saying what it shows is the extreme heat wave in Central Europe, principally in France and Spain, which killed more than 35,000 people in the summer of 2003, was an extreme event in 2003. It's the asterisk at the top of that spike, just past the year 2000. And what these projections show is that under business as usual, a heat wave of that magnitude will occur once in 2 years by 2040. Every 2 years there will be a heat wave of that severity in 2040. And by 2070, those conditions will be unusually cold for Central Europe in the summer. That's where we're heading under business as usual. Higher temperatures also mean more smog, a matter that ought to be of some concern in Beijing. The higher the temperature, the worse the smog formation. Higher temperatures ultimately mean reduced productivity in agriculture. These are simulations of the productivity of corn and wheat in temperate zones as a function of how much the local temperature increases. And what you see here is that the yields start dropping when local temperature increases reach 1 to 2 degrees Celsius. This is actually assuming an increase in rainfall, but in fact, drought is a real possibility and makes these projections worse. In fact, if you look at the drought projections, they are stunning. These are drought projections for a mid-range scenario of the IPCC. All you have to know about the scale is that as it goes from yellow to orange to red to brown, drought is getting more and more severe. And you see that by late in the 21st century, severe drought is expected over much of the world as a result of these changes in the climate. Another thing that is coming that people have until recently not paid very much attention to is that in addition to warming the oceans, we are making the oceans more acid. The reason we're doing that is when you add carbon dioxide to the atmosphere, some of it dissolves in the ocean and it forms carbonic acid. And that actually lowers the pH of the ocean, makes the oceans more acidic. That's why I say sometimes we're pickling the oceans, making the oceans more like vinegar. And that makes it more difficult for all of the organisms that make skeletons or shells out of calcium carbonate to do that. And so, among other things, we are making the oceans inhospitable to coral reefs, as well as to shrimp, to crabs, to lobsters, and a lot of other things that we eat a lot of. This should be of great concern. It is on track, under business as usual, to make most of the world's oceans incapable of supporting coral reefs by the middle of this century, and nobody knows for sure what the tipping points are going to be in terms of drastic impacts on populations of shrimp, of crabs, of scallops, of oysters, and so on. If you look at the sea level rise problem, which really in a way might be the ultimate consequence of climate change, we know that if we manage to melt all of the ice in the Greenland and Antarctic ice sheets, that sea level around the world would go up by about 70 meters. That would probably take thousands of years, even in a greatly warmed climate. But we do know from reconstructing past climates that twice in the last 19,000 years, for natural reasons, sea level went up at rates ranging from 2 to 5 meters per century. We also know that the magnitude of the influences that humans are now exerting on the climate is greater than the magnitude of the influences that caused those previous rapid sea level rises. And so there is reason for concern that rapid sea level rises are possible. No one knows what the odds are. The models that we have of sea level rise are not capable today of figuring out how the mechanisms work that would produce these very rapid rises. They would have to be based on slippage of the ice sheets into the ocean, not just on melting. But we simply don't know how rapidly this could happen. We do know that the most vulnerable of the ice sheets are the Greenland ice sheet, The Greenland ice sheet contains about 7 meters of sea level rise. The other most vulnerable sheet is the West Antarctic ice sheet. That has another 5 meters. If we lost those together, that would be 12. And again, if we lost everything, that would be 70. And you see here what this would do to the state of Florida and surrounding areas in the United States. I wish I had a diagram showing what it would do to China, but it would be equally impressive. So that takes us to what could we do? We have basically 3 options confronting this problem. One option is mitigation. That's a word that means steps that you take to reduce how much climate change you get. Steps that you take to reduce the pace and the magnitude of the changes in global climate that are being caused by human activities. The second option is adaptation. That means steps that you take to reduce the harm to human well-being that result from the changes in climate that do occur, from the changes in climate that you do not succeed in avoiding by mitigation. And the third option is suffering. It really is that simple. There are only 3 options: mitigation, adaptation, and suffering the consequences of the changes in climate that you do not succeed either in avoiding through mitigation or adjusting to through adaptation. It's important to understand concerning those 3 options that we're already doing some of each. In China, in the United States, and elsewhere in the world, we're already doing some mitigation. We're already taking steps to reduce our greenhouse gas emissions. We're already doing some adaptation. We're changing agricultural patterns to cope with climate change. We're building more dams and dikes to deal with floods and sea level rise. And we're already doing some suffering, as I've pointed out, in looking at the wildfires, the droughts, the impacts on human health. The question for the future is what the mix is going to be of mitigation, adaptation, and suffering as we move forward. And minimizing the amount of suffering in that mix can only be achieved if we do a lot of mitigation and a lot of adaptation. We have to do a lot of both. Relying on mitigation alone is not going to work because climate change is already occurring, and no matter what we do, we cannot stop it quickly. Relying on adaptation alone will not work because adaptation gets more difficult and more expensive and less effective the larger are the changes in climate to which you're trying to adapt. You ask somebody who lives in a low-lying island, how are they going to adapt to 2 meters of sea level rise? That's not adaptation, that's evacuation. Clearly what we need is enough mitigation to avoid unmanageable climate changes and enough adaptation to manage the changes that are unavoidable. That's the mix that we need. Now, some key realities about mitigation. First of all, human emissions of carbon dioxide are the biggest piece of the problem. They're more than half, and they are getting larger as a share of the problem. Of those human emissions of carbon dioxide, 3/4 are coming from burning coal and oil and natural gas, and those sources are about 80% of the world's energy supply. And about 1/4 of the carbon dioxide is coming from deforestation in the tropics. About 60% of the fossil carbon dioxide was coming from industrialized countries in 2006. That is, of the CO2 that was coming from burning fossil fuels, 60% of it was from the industrialized countries 2 years ago. But the developing countries will soon take over the lead because they are growing faster. This is not a race that you should want to win, but you're winning it anyway. A third reality that's very important is that we cannot change the global energy system that is responsible for these emissions very quickly. It represents a huge capital investment. About $15 trillion has been invested in the global energy system that we already have, and normally that investment turns over in about 40 years. That's the average lifetime of a power plant, an oil refinery, any other major energy facility. If you've got a $15 trillion investment that turns over in 40 years, you can't change it overnight, no matter what you do. And the deforestation part of the problem is also not very easy to solve quickly, because the forces that are driving deforestation in the tropical countries are forces that are very much a part of the economics of food, of fuel, of timber, of trade, indeed the economics of development itself, are driving deforestation. Oops, wrong direction again. This is a figure from the Intergovernmental Panel on Climate Change just showing the distribution of all of the greenhouse gas emissions in the world in 2004. Those that come from the energy supply system, from electric power plants, from oil refining, those that come from the use of energy, transport, buildings, industry, and those that come from agriculture and forestry. If you added it up, you would see that energy was about 2/3 of it altogether. If you want to know where all that energy growth came from, here's the picture of the last 150 years of energy growth, a 20-fold increase in the world's use of energy over 150 years, and nearly all of it driven by the expansion of coal and oil and natural gas. This shows the breakdown of the recent energy growth by region, North America, Latin America, Europe, the Eastern European and centrally controlled economies, the Middle East, Africa, and finally Asia, the most rapidly rising of them all. The carbon dioxide emissions, of course, have grown in proportion because they're coming primarily from the burning of fossil fuels. This shows the carbon emissions from deforestation over the same time period, the last 150 years. Deforestation has essentially stopped outside the tropics, but the tropics have more than taken over, as you see in this picture. If you look at the greenhouse gas emissions for selected countries, in 2005 the United States was still in the lead, China close behind, Indonesia and Brazil in the next two places, not because they burn a lot of fossil fuels, they don't, but because they're doing a huge amount of deforestation. Then comes Russia, India, Japan, and so on. Also shown there are the annual growth rates, and those annual growth rates are such that it has been estimated that China passed the United States as the biggest emitter in 2007. This just gives the breakdown, how much from energy, how much from agriculture, how much from deforestation in some of the major emitting countries. I won't say much about this. You can look at it in your notes. This points out that even though China may have passed the United States as the biggest emitter, they are still far below the United States in emissions per person because, of course, China has a lot more persons. High energy growth is expected to continue under business as usual between now and 2030. World energy will increase by about 50%. China's energy use is expected to double. Electricity growth is expected to be even more rapid. And fossil fuels are expected under business as usual to continue to be the principal sources of energy for the world. That is bad news from the standpoint of greenhouse gas emissions. The projected growth in electric power plants that burn coal is especially high. These are the figures projected out to 2030 for the United States, China, India, and the whole world. Coal burning capacity for the whole world nearly doubles in this period. A very substantial chunk of that growth, very substantial part of that growth takes place in China and secondarily in India. So what are our options? What could we do about this? Certainly we could reduce the emissions of greenhouse gases and soot, black particles from the energy sector. We could reduce deforestation and increase reforestation. We could modify our agricultural practices to release less greenhouse gas and to build up the amount of carbon stored in the soil instead of put into the atmosphere. There's some other things we might do if we got desperate enough. We might try to remove, that is, to filter greenhouse gases out of the atmosphere. Very difficult technically, but it is possible. It would be very expensive, much more expensive than filtering it out of the exhaust gases of power plants. We might even get desperate enough to try what is called geoengineering, re-engineering the earth to try to compensate for the changes in greenhouse gases, basically by making the earth more reflective, so it would send more sunlight back to space. One way to do this would be to inject reflecting particles into Earth orbit so that less of the sunlight would get through to the surface of the Earth. This has enormous problems of cost and potential side effects, but again, it might be considered if we get sufficiently desperate to try to stop the pace of climate change. How much mitigation do we need? Well, we have a United Nations Framework Convention on Climate Change, which 191 countries have ratified, including China and including the United States. That convention calls for stabilizing greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous human interference in the climate system. The trouble is, when that treaty was negotiated in 1992, nobody agreed on what dangerous meant. What is the definition of dangerous that we are trying to avoid? Nobody agreed on what level of greenhouse gas concentrations would correspond to dangerous interference. And in fact, there is still no official agreement on what is dangerous. But I believe, based on what I have already told you, that the current level of human interference in the climate system is dangerous. If 150,000 premature deaths in the year 2000 is not already dangerous, then we have some new definition that is needed of what danger means. I think the issue now is whether we can avoid catastrophic human interference in the climate system, completely unmanageable interference with consequences escalating out of control. As I already mentioned, the temperature would rise another 0.5 degree centigrade to something like 1.3 above the pre-industrial level, even if we could stabilize concentrations today, and we can't. And the chance of a tipping point, of crossing a threshold into catastrophic change, get bigger as the average surface temperature increase gets more than 2 degrees C above pre-industrial. That is what led the Europeans to the conclusion that we should try to avoid exceeding 2 degrees C. That is probably the most prudent target that still might be attainable, and as you'll see, it's not going to be easy to attain. This is a picture of the emissions paths out to 2100 that would correspond to stabilizing the atmospheric concentration of carbon dioxide at a level that would give you a 50% chance of not exceeding 2 degrees Celsius in the global surface temperature increase. The temperatures are different because they depend on differences and uncertainties in how the natural carbon cycle is treated in the models, and they differ in choices about whether you put most of the burden earlier or later in the trajectory. Do you let it go up for a while and then rise more steeply, or do you start to level off the curve sooner and let it shrink more gradually? What you see in the middle, that blue triangle, is where business as usual emissions would take us by 2050. And you see that to be on a trajectory for 450 parts per million, you need to be at about half the level of business as usual by 2050. This is a huge challenge. How can you get there? If you look at, in very simple algebraic terms, of where the emissions are coming from, they're coming from 4 things. They come from the number of people, the P factor. They come from the amount of economic activity per person, GDP per capita. They come from the amount of energy used to get a unit of gross domestic product, E over GDP. And they come from the carbon dioxide intensity of energy supply, how much carbon is released to the atmosphere for each unit of energy that you provide to the economy. This is simple algebra. It's not controversial. It's what in mathematics is called an identity. It is identically true. And the only interesting question is, what can we learn by looking at the individual factors about the possibilities for reducing the growth? Obviously, a number of things come to mind in terms of options for reductions. We could reduce population growth. We could reduce the growth of GDP per person. We could reduce the ratio of energy to GDP. We could improve the energy efficiency of the economy, and we can do that in a number of ways. We can do it by improving the efficiency of energy use. We can do it by increasing the technical efficiency. We can do it by changing our mix of economic activities. And finally, we could reduce the amount of carbon dioxide that gets released for each will increase by about 50%. China's energy use is expected to will increase by about 50%. China's energy use is expected to double. Electricity growth is expected to be even more rapid. And fossil fuels are expected, under business as usual, to continue to be the principal sources of energy for the world. That is bad news from the standpoint of greenhouse gas emissions. The projected growth in electric power plants that burn coal is especially high. These are the figures projected out to 2030 for the United States, China, India, and the whole world. Coal burning capacity for the whole world nearly doubles in this period. A very substantial chunk of that growth, very substantial part of that growth takes place in China and secondarily in India. So what are our options? What could we do about this? Certainly we could reduce the emissions of greenhouse gases and soot, black particles from the energy sector. We could reduce deforestation and increase reforestation. We could modify our agricultural practices to release less greenhouse gas and to build up the amount of carbon stored in the soil instead of put into the atmosphere. There's some other things we might do if we got desperate enough. We might try to remove, that is, to filter greenhouse gases out of the atmosphere. Very difficult technically, but it is possible. It would be very expensive, much more expensive than filtering it out of the exhaust gases of power plants. We might even get desperate enough to try what is called geoengineering, re-engineering the Earth to try to compensate for the changes in greenhouse gases, basically by making the Earth more reflective, so it would send more sunlight back to space. One way to do this would be to inject reflecting particles into Earth orbit so that less of the sunlight would get through to the surface of the Earth. This has enormous problems of cost and potential side effects, but again, it might be considered if we get sufficiently desperate to try to stop the pace of climate change. How much mitigation do we need? Well, we have a United Nations Framework Convention on Climate Change, which 191 countries have ratified, including China and including the United States. That convention calls for stabilizing greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous human interference in the climate system. The trouble is, when that treaty was negotiated in 1992, nobody agreed on what dangerous meant. What is the definition of dangerous that we are trying to avoid? Nobody agreed on what level of greenhouse gas concentrations would correspond to dangerous interference. And in fact, there is still no official agreement on what is dangerous. But I believe, based on what I have already told you, that the current level of human interference in the climate system is dangerous. If 150,000 premature deaths in the year 2000 is not already dangerous, then we have some new definition that is needed of what danger means. I think the issue now is whether we can avoid catastrophic human interference in the climate system, completely unmanageable interference with consequences escalating out of control. As I already mentioned, the temperature would rise another 0.5 degree centigrade to something like 1.3 above the pre-industrial level, even if we could stabilize concentrations today, and we can't. And the chance of a tipping point, of crossing a threshold into catastrophic change, get bigger as the average surface temperature increase gets more than 2 degrees C above pre-industrial. That is what led the Europeans to the conclusion that we should try to avoid exceeding 2 degrees C. That is probably the most prudent target that still might be attainable, and as you'll see, it's not going to be easy to attain. This is a picture of the emissions paths out to 2100 that would correspond to stabilizing the atmospheric concentration of carbon dioxide at a level that would give you a 50% chance of not exceeding 2 degrees Celsius in the global surface temperature increase. The temperatures are different because they depend on differences and uncertainties in how the natural carbon cycle is treated in the models, and they differ in choices about whether you put most of the burden earlier or later in the trajectory. Do you let it go up for a while and then rise more steeply, or do you start to level off the curve sooner and let it shrink more gradually? What you see in the middle, that blue triangle, is where business as usual emissions would take us by 2050. And you see that to be on a trajectory for 450 parts per million, you need to be at about half the level of business as usual by 2050. This is a huge challenge. How can you get there? If you look at, in very simple algebraic terms, of where the emissions are coming from, they're coming from four things. They come from the number of people, the P factor. They come from the amount of economic activity per person, GDP per capita. They come from the amount of energy used to get a unit of gross domestic product, E over GDP. And they come from the carbon dioxide intensity of energy supply, how much carbon is released to the atmosphere for each unit of energy that you provide to the economy. This is simple algebra. It's not controversial. It's what in mathematics is called an identity. It is identically true. And the only interesting question is, what can we learn by looking at the individual factors about the possibilities for reducing the growth? Obviously, a number of things come to mind in terms of options for reductions. We could reduce population growth. We could reduce the growth of GDP per person. We could reduce the ratio of energy to GDP. We could improve the energy efficiency of the economy, and we can do that in a number of ways. We can do it by improving the efficiency of energy use. We can do it by increasing the technical efficiency. We can do it by changing our mix of economic activities. And finally, we could reduce the amount of carbon dioxide that gets released for each unit of energy provided to the economy in a number of different ways. We could use more natural gas, which releases less carbon dioxide than oil or coal. We could do it by replacing fossil fuels with renewable energy. We could do it by replacing fossil fuels with nuclear energy. And we could do it by modifying the fossil fuel technologies to capture the carbon dioxide rather than releasing it into the atmosphere and sequestering it under the ground or under the oceans. This is essentially the whole array of possibilities. There's nothing else. Okay? We have to choose somehow from this list. And there is no easy answer because all of those options have limitations and liabilities. And I'll just go through them very quickly here because I know I'm going too long and I want to get to the end. But each of these has liabilities, and you can just read them here as I'm going through them. I'll have to explain this one. Wind, it's a wonderful energy source, but it's intermittent. That means the wind doesn't blow all the time. And sometimes there are controversies over putting up windmills. In the United States, we have a term we call NIMBY, which stands for not in my backyard. It means don't do this anywhere near me. You can have a windmill as long as you don't put it in my backyard. There's a new term that is emerging that's called banana, and that stands for build absolutely nothing anywhere near anybody. And this reflects an attitude that is inconsistent with providing the energy that society needs in order to be prosperous. People need to understand that electricity does not materialize magically behind the wall plug, that it has to be generated somewhere. Somebody has to build and operate something somewhere if there's going to be any energy. Biofuels, very interesting, but there are problems of net energy, land use, and competition with food. Solar photovoltaic cells, they're wonderful, but the sun doesn't shine all the time. They're expensive. Nuclear fission, the current form of nuclear energy, has challenges in cost, waste, safety, and proliferation. Nuclear fusion doesn't work yet, big problem. Works in the sun, but we have not made a fusion reactor that works on Earth. Capturing and sequestering the carbon dioxide is expensive. You have to do it on a very large scale. It's complicated. Hydrogen energy, very interesting, but it's a way to store energy, not a way to produce it. You have to make hydrogen from something else, and then you need a big infrastructure to store it and transport it. And improving end-use efficiency, which in many ways is the best option, requires a lot of education. Billions of consumers have to know what their options are and what it makes sense to do if you're going to get the full potential from efficiency. Now, if you have a big problem and you have no panacea, that doesn't mean you don't do anything. It means you need a portfolio of approaches. You need to do a lot of things at once, not just one or two things, but many different things, so that you can compensate for the different shortcomings of the different possibilities. We also need to do increased research and development on all of the options to try to improve them, to reduce their limitations, to improve their performance, to lower their costs, to reduce their adverse side effects, so that the menu we can choose from in making a portfolio of solutions will be better in the future than the menu we have today. Ultimately, to solve this problem, deployment of these technologies is going to have to take place on an enormous scale. I already showed you the trajectories that indicate that 450 part per million trajectory means that global carbon dioxide emissions have to be 7 to 9 billion tons of carbon per year lower than business as usual by 2050. And you can get an idea of what that means with some different examples of what it takes to avoid 1 billion tons. To avoid 1 billion tons a year, and remember we need 7 to 9 of these in 2050, to avoid 1 billion tons, all the buildings in the world have to be 20 to 25% more efficient in 2050 than they would be under business as usual, which already includes quite a lot of improvement. To save 1 billion tons, 2 billion automobiles have to get 60 miles per gallon instead of 30. To avoid the emissions of 1 billion tons, 800 large coal-burning power plants have to be capturing and sequestering their carbon dioxide. There are only 1,100 of those power plants in the world today. You need 800 of them to be capturing and sequestering carbon to avoid 1 billion tons. Or you need 700 large nuclear plants to replace coal-burning plants to avoid 1 billion tons a year. Or you need 1 million large wind turbines. 1 million large wind turbines to avoid 1 billion tons a year. Or 2,000 large photovoltaic power plants to do it. So we don't just have to think big, we have to think huge in thinking about how much has to be deployed to solve this problem. Now there are also options for adaptation. We can change cropping patterns, develop heat-resistant crop varieties, strengthen our defenses against tropical diseases, build new water projects, dikes and storm barriers, avoid building more buildings and settlements on floodplains and near sea level. Many of these are things we ought to do anyway. They're just good sense in a world with variable weather. And so they are win-win in that sense and should be relatively easy to do. But again, they won't be enough if we don't also reduce the amount of climate change itself. Turning quickly to the economics, some good news is that there are large and inexpensive emissions reductions that are available from increasing the efficiency with which we use energy in buildings, in industry, and in the transport sector. And those improvements are often win-win in that the co-benefits in the value of the saved energy, increased domestic jobs, increased energy security, reduced pollution, make them worth more than what they cost. They're worth doing even if you weren't worried about climate change. There are also some mitigation options on the supply side that meet that standard. That is, that they pay economically even under current circumstances. And so we should be willing to do them even if we weren't worried about climate change. But the bad news is that the win-win approaches won't be enough. Doing enough mitigation to solve this problem requires putting a price on greenhouse gas emissions so that there is an incentive to do the more expensive things. And this is summarized very quickly, and because of the time I won't elaborate on this, but this is a supply curve for avoided greenhouse gas emissions in the year 2030, developed by the international consulting company McKinsey. And the bars that are below the line are measures that would be profitable under current circumstances, and the measures that are above the line, further to the right, are measures you have to pay a penalty for under current circumstances, and the higher the bar, the higher you have to pay to avoid those emissions. And what this shows is that to be on the 450 part per million trajectory, you have to pay quite a lot in 2030 for the emission reductions that you're ultimately going to need. Can we afford it? Well, you can do a simple calculation. Current carbon dioxide emission rates amount to 10 billion tons of carbon in CO2 per year. If we were paying $100 a ton to avoid half of it, which is at the upper end of the McKinsey curve, that would be $500 billion a year, $500 billion a year. That's under 1% of the global world product. And much of that would be a transfer. It's not money that actually disappears. The world, by comparison, spends 2.5% of economic product on defense. The United States spends 5% on defense. It's hard to believe that we couldn't afford, if we wanted to spend 1% solving the climate problem. More sophisticated models get similar results. They say that the cost of mitigation to stabilize at a respectable level would be somewhere in the range of 0.5% to 2% of world GDP in 2030, 2050, and 2100. It's a lot of money in absolute terms, but it's not something the world could not afford to do. And you have to ask the question, can we afford not to? Some people argue, in fact, that a transition to sustainability in terms of climate could create a new economic boom with new innovation, new jobs, and so on. But in any case, if you focus on whether the needed mitigation and adaptation are going to cost money or make money, that really misses the key comparison. The key comparison requires asking, what is the cost to the economy if we don't fix the climate problem? What is the damage that will be done to our societies? The economic damages of not stabilizing climate are incalculable, and I mean that literally. We don't know how to calculate them, but there is every reason to believe that they are much greater than even the most pessimistic costs of fixing it. So what do we need to do? 2 minutes of policy realities and then I'm done. The industrialized nations have got to lead in implementing the costlier solutions. We have to go first. We have to pay more of the upfront costs, and we have to provide assistance to the developing countries. That's a matter of historical responsibility. We cause most of the problem. It's a matter of capacity, of equity. It's a matter of existing international agreements. The Framework Convention recognizes differentiated responsibilities. Secondly, we're going to have to compensate developing countries for not cutting down their forests. If we don't do that, the forests are all going to be cut down, and the climate change problem is going to be insoluble. Third, we are going to need a formal and binding agreement on the allocation of emissions in the post-2012 period, and ultimately, such an agreement can only be based on equal per capita emissions rights. There is no other long-term solution that the whole world is going to accept. The most important next steps, we have to accelerate the win-win measures. We need to put a price on greenhouse gas emissions in the industrialized countries so that we can start working to find the cheapest solutions. We need, in the UN process, to complete a new global framework by 2009 so that it will be ready to go into place after 2012. We need to be increasing our investments in research and development and demonstration by 4 to 10-fold. And we need to expand international cooperation on deploying advanced energy technologies starting immediately. The single most important step is that the United States, historically and cumulatively the biggest emitter, needs to stop lagging and start leading. China has a big role in the solutions for a number of reasons. I list them very quickly here. Good education system, high production of scientists and engineers, an environment that favors rapid innovation. Global role is growing, and that means other countries want to cooperate with the countries in Asia to solve these problems through cost sharing and technology transfer. The high rate of growth of the Chinese economy allows for the dominance of new efficient technologies and infrastructure over old and inefficient ones. That and other factors position China to be a world leader in renewable energy and energy efficiency and in clean coal. And the underdeveloped rural regions provide an opportunity to plan and build new resource-conserving towns. I think China is going to have a big role in solving this problem. There are some references, and finally I'm done. Thank you very much.